All right. Okay. Maybe. Man, this thing never works in this hour. I don't know what it is. Okay. Okay, we're going to start in this forces, motion, and energy text. So if you hopefully you've written your name in it. Oh no, I'm gonna pause right now so you guys can give me your book numbers. That's my ABB for you. Okay, today we're just gonna get an idea of where we're going here. So in this forces, motion, and energy, there are 6 chapters. Matter and motion, forces in motion, forces in fluids, work in machines, energy and energy resources, and heat technology. Yes, we're gonna fly through this, guys. It's very important that you learn multiple ways of learning, so we're kind of switching gears a little bit and going into text. So we've got to learn some skills here. All right, so you're going to be keeping a silent science log. We're going to be answering questions in this science log, and we're going to start with chapter 1. So as we are going through, my suggestion to you is to be maybe taking notes, even if it just happens to be the headings. Remember, when we take notes, we should always start by writing the date. So today is 10/17/22. We are in chapter 1. So you can abbreviate things if you want, maybe just CH1, matter in motion. Let me turn this light off. Is that better? I'm writing exactly what's in your text. I'm on page 2 in your text. Are you in page 2 in your text? So I noticed there's a really fun startup activity. Let's plan to do that tomorrow. I'll set a note that we are going to use dominoes tomorrow. Dominoes, not the pizza. You should do that. Did someone say pizza? All right, so tomorrow we're gonna work on speed with our dominoes. We're gonna see how long the total length of our row is, and then see how fast it goes down. And we're gonna take length divided by the time and find its speed. Okay, so you see right away under matter and motion, we have 4 different sections. 1, 2, 3, 4. Those sections and those headings are very important to cue us to what am I trying to learn here, right? In those sections. There will also be questions under those sections that we're going to be reading. Okay? Excuse me, sorry. Measuring motion. So today, as we're getting used to our text, I'm going to be reading, but as the week goes on,
We are going to be.
Let's go. I mean, no one wants to listen to me forever. All right, so section 1. Section number 1 is measuring motion. So I'm going to go ahead and write that down. We might have words within this section we need to know, or important concepts that we might need to highlight. All right. Does everyone see where we are? Do you see we're gonna have some terms here? You can't write anymore? Guys, you gotta get ready for high school. The goal is to be challenged now when the stakes are low, so that next year when the stakes are higher, that you are ready to roll. We're on page 4. Look around you. You're likely to see something in motion. Your teacher may be walking across the room, or perhaps a bird is flying outside a window. Even if you don't see anything moving, motion is still occurring all around you. Tiny air particles are whizzing around. The moon is circling the earth and blood is traveling through your veins and arteries. Observing motion. You might think that the motion of an object is easy to detect. You just observe the object. But you actually must observe the object in relation to another object that appears to stay in place. Have you ever felt like when you were in a car and you started moving, but you weren't like going anywhere because maybe a car next to you started backing up or a car next to you started going? And it's a really weird phenomenon, right? So the object, you have to think about it in relation. So that's why sometimes people fight their speeding tickets. Because if a police cruiser is not stationary, they don't really have much equipment to figure out the speed. They're figuring out relative speed. And if they're going this way and you're going the other way, it actually looks like they're going a lot faster. You want to try another pencil or you just give it up? Okay.
I'm writing this. I'm writing this.
So the object that appears to stay in place is a reference point. So I see highlighted things. I'm just going to write down reference point. And then I'm going to use my own words and say object in place.
I'm writing this.
What are you doing? You're writing with a piece of wood?
Yeah.
When an object changes position over time when compared with a reference point, the object is in motion. So I'm starring this because it's a purple word, motion. Purple. The definition of motion is written there for us. Sorry, there's kind of a shadow because of my notebook.
This is my son.
All right. An object is in motion when compared with a reference point, it's changing positions. So how would we define motion? Sometimes I have a hard time rewording it, so I'm just defining the word and not just picking it out of a sentence. So we have these handy dandy glossaries, right? Looking up motion. You see it? This is on page 224. An object's change in position over time when compared with a reference point. So that's what I'm going to write.
I did.
All right.
Maybe the slide.
Okay, get it together. An object's, this is a lot. An object's, page 224. I went to the glossary. Oh, where did that come from?
No way.
How do I get rid of them? An object's change in position over time when compared to or with when compared with a reference point. Guys, this is excellent for your writing skills, for your spelling skills, for your grammar skills, for your reading skills. They will. The more you read, the more you see things, the more you'll realize how those
My
things are.
handwriting will never get
Right. It never will.
Mine says the exact same, it's like
That's not good.
I've been
All right,
getting progressively better.
question about motion. Remember, we had to define reference point because that was in our motion definition. So even though reference point wasn't as important as motion to us, it was still important to understand motion. We had to know what a reference point was. All right. Let's go back to our section here. Truth and fact. There's a lot of stuff going on here. All right, back to page 4. We just defined motion. When an object is in motion, you can describe the direction, page 4, you can describe the direction of its motion with a reference direction, such as north, south, east, west, or up and down, or right and left, forward, backward, right?
Bro, what is that?
You're in chapter 3 already. We're in chapter 1.
I finished off that.
This is chapter 1, section 1. All right, the Earth's surface is a common reference point for determining position and motion. So non-moving objects on Earth's surface, such as buildings, trees, and mountains, are also useful reference points, as shown in figure 1. So looking at this figure 1, during the time it took for these pictures to be taken, the hot air balloon changed position compared with the reference point. The mountain. We know mountains don't move on their own, right? We use them as reference points. Have you ever heard someone give you directions and they're like, drive down to Wendy's and turn left, or things like that? They're using those as reference points. They're not just suddenly going to disappear. They're stationary. Yes. Well, it might move based on an earthquake, right?
Not gonna move on my own. It was like.
All right, so a moving object, the second paragraph under the common reference points, a moving object can also be used as a reference point. For example, if you were on the hot air balloon shown below, you could watch a bird fly by and see that it was changing position in relation to your moving balloon. Furthermore, Earth itself is a moving reference point. It is moving around the sun. Okay.
So is the mountain really stationary?
Yes, but the Earth is moving. You see here. I guess. So speed. Here's another important purple word. Speed depends, listen carefully. Speed depends on distance and time. So the rate at which an object moves is its speed. So I got another star here. And we have another word here. It is speed. The rate at which an object, oops, forgot my B. Object moves. I'm just copying down those words from my text. If I was struggling to know what to write, remember we can always go back and refer to the glossary. Speed. All right. Speed depends on the distance traveled and the time taken to travel that distance. Look back at figure 1. Suppose the time interval between the pictures was 10 seconds and the balloon traveled 50 meters. And that time, the speed, distance divided by time of the balloon is 50 meters per 10 seconds, or 5 meters per second. So let's write out.
Kyle's moving at 140.
Or Kaya in this case. Kaya. Oh. Let's write this down.
Wait. Stop moving my desk. Oh, yeah.
It could be worse. All right, let's write this equation. So speed is equal to what did they tell us? Is equal to distance divided by time. Distance divided by time. So you know how I would write that?
300 million.
S is equal to D divided by T.
Scientific notation. I don't know, or doing the math. That was called scientific notation.
Yes, you're right. All right, so speed is equal to the distance divided by time. This will be very important tomorrow because you're gonna figure out the speed of the dominoes falling. Can you stop? Thank you. Speed, speed, speed. Important, 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 right? All right. So looking at our text. Is it easier over here? The SI unit for speed is meters per second, kilometers per hour, feet per second, and miles per hour are other units commonly used to express speed. Okay? Determining average speed. Most of the time, objects do not travel at a constant rate, right? When you're driving through town, you have to stop at stop signs.
You don't have to.
It's
It's just a strongly enforced recommendation.
Yeah, strongly enforced.
You won't die. You won't die.
Yeah.
This is recommendation.
All right. So, guys, come back. Most of the time, objects do not travel at a constant speed. For example, you probably do not walk at a constant speed from one class to the next, right? You might see a friend and slow down, or you might have to get around people. You might stand around and talk to your friends.
We're walking actually like
So-
walk. Yeah.
Therefore, those sixth graders, they tell you.
They walk so slow.
I'm so glad I don't have any classes.
Maybe I should be complaining about the eighth graders right now. All right. It's very useful. It is very useful to calculate, here we are, average speed using the following equation. Average speed equals total distance divided by total time.
You should use the other mic.
So we are, then I have to hold it and I can't hold it anyway. So we're gonna kind of change this a little bit. Average S equals total D divided by total T. Because sometimes it's not constant. If you're on the expressway and your parents set their cruise control, then it's a little bit more constant, right?
I don't know how to spell total.
Total, T-O-T-A-L.
Total? T-O-T-A-L. T-O-T-A-L.
Do you guys remember what that fraction bar means? This is my math self. It means divided by.
Division.
Multiplication.
Subtraction. It's like,
Addition.
this is like a subtraction.
Not a subtraction thing, my dear. No, not how this is. Fraction bar divided by, yes, you guys are big kids now. The opposite of multiplication, the inverse of multiplication. The reciprocal multiplicative inverse. Correct, of the same number. Repeated subtraction instead of repeated addition, you got it. All right, recognizing speed on a graph. Suppose a person drives from one city to another. The blue line in the graph below shows the distance traveled every hour. Notice that the distance traveled every hour is different. This is because the speed is not constant. The driver changes speed often because of weather, traffic, or varying speed limits. The average speed can be calculated by adding up the total distance and dividing it by the total time. So do you see they took the total distance and divided by the total time, and that gave them the average. So 360 kilometers was total traveled over the 4 hours. You see, sometimes they were traveling faster, sometimes they were traveling slower. The red line shows the average. Or the average distance traveled each hour. All right, we're gonna take a math break.
Wait, what?
Math break. No. Number 1. Practice calculating the average speed. If you walk for 1.5 hours and travel 7.5 kilometers, what is your average speed? Yes, we have lots of calculators on the window. Not times. How do we calculate our average speed? Distance divided by time. Remember, speed is distance divided by time, which is equal to, what is my distance? 7.5 kilometers divided by, what is my time? 1.5 hours.
1 hour and 30 minutes.
You got it.
It's 5.
All right, so 7.5 divided by 1.5 is
5.
5 what?
This is my answer.
Kilometers per hour. Remember, we can label with the slash. That slash means per, also means divided by. We took the kilometers divided by the hour. You guys probably haven't seen a whole lot of rates lately. We did a lot of that in 6th and 7th grade.
Then?
Yeah.
Okay, no, I'll go with it.
Ratios. All right, relationships.
Not for a unreasonably long
All right, number 2, a bird flies at a speed of 15 meters per second for 10 seconds, 20 meters per second for 10 seconds, and 25 meters per second for 5 seconds. What is the bird's average
Nah,
speed?
no, that's too much.
Well, we have to figure out how far they went. So 15 meters per second times 10 seconds is 150 meters. Look, your seconds cancel out, right? Plus 20 meters per second for 10 seconds.
Suck at this.
Again, your seconds cancel out. What's 20 times 10? 200 meters.
So,
You're fine.
I asked him for the 5.
Yes.
What?
Top 2. And then if we have 25 meters per second times 5 seconds. Again, seconds cancels and we're left with meters. What's 25 times 5? If I have 5 quarters, I have $1.25. So if we add these up, 0 plus 0 plus 5, 5 plus 0 plus 2, 1 plus 2, 3, 4, 475 meters divided by how many seconds? Well, this was 10, plus 10 is 20, plus 5 is 25. What is this speed? Put it into your calculator. 475 divided by 25. 19 meters per second? We good there?
Yes.
Yes, we're good there. Is that what you guys got?
Perfect for the.
Guys, it was a little tricky for sure. No, that's not all you have to do. We gotta keep cruising. That was just a break. That was just our math break. I don't know.
My eraser fell out of my pencil.
Your eraser flew out of your pencil. Alright, I'm not sure where you are, but I do have to turn my page, guys. When you turn your page, please go directly to the next page or the back of this page. Don't skip around in your notebook. Stay organized in your notebook. Okay. I will, no problem. Kai, your dad's here, honey.
Bye, Kyle.
All right, I'm turning to page 6 and so should you. We're gonna look at velocity. So now with the speed and adding to the speed, we're having direction. So speed does not include direction, but velocity does. Are you ready? Here's a riddle for you. Two birds leave the same tree at the same time. They both fly at 10 kilometers per hour for 1 hour, 15 kilometers per hour for 30 minutes, and 5 kilometers per hour for 1 hour. Why don't they end up at the same destination? Why don't they end up at the same destination? No, they're going at the same speed. Why don't they end up at the same destination? They went in separate ways. That's a good one. Have you figured it out? The birds traveled at the same speeds for the same amounts of time. Guys, I should see you on page 6. 6. 6. Page 6. The birds traveled at the same speed for the same amounts of time, but they did not end up at the same place because they went in different directions. In other words, they had different velocities. The speed of an object in a particular direction is the object's velocity. What's that word?
Velocity.
Velocity. There's another purple word. That means we have to write it down.
Gravity.
Velocity. So this is the speed of an object. Speed of an object in a particular direction. Guys, stay focused. We got a little bit of time left.
What's a semiotic error?
You know what it means? It means an operator error.
I'm not an operator.
Yeah.
You know the sign up page?
All right, be careful here not to confuse the term speed and velocity. They do not mean the same thing.
They don't?
They do not mean the same thing. Speed and velocity do not mean the same thing.
I would always say.
Because velocity must include direction, it would not be correct to say that an airplane's velocity is 600 kilometers per hour. However, you could say the plane's velocity is 600 kilometers per hour south. Velocity always includes a reference direction.
Oh.
So now we have reference point and reference direction. So we got to know which direction we're going when we're talking about velocity. All right, so figure 2 further illustrates the difference between speed and velocity. So let's look. The speeds of these cars may be similar, but their velocities are different because they are going in different directions. Some are going this way, some are going this way, some are going that way, and all over, right? So their velocities are different because their directions are different. Velocity changes as speed or direction changes. You can think of velocity as the rate of change of an object's position. An object's velocity is constant only if its speed and direction doesn't change. So if I'm going in this at the same speed, but I turn, my velocity is changing. If I'm going in the same speed, but I don't turn, my velocity is constant. For example, if a bus is traveling at 15 meters per second south, speeds up to 20 meters per second, a change in velocity has occurred. But a change in velocity also occurs if the bus continues to travel at the same speed, but changes direction to travel east. All right, self-check here. Which of the following are examples of velocity? So I'm going to write examples. You can just write EX if you know that it stands for examples. Examples of velocity. Which of the following? 25 meters per second forward? Does it have a speed and direction? Yes, so we can include that. 25 meters per second forward. So there's one. How about number 2? 1,500 kilometers per hour. Is that an example of velocity?
No.
No, what's it missing?
Direction.
The direction. How about number 3? 55 meters per hour south.
Yes.
Yes,
Is that 55?
55 meters per hour south. I mean, you could argue that forward doesn't give you a relative direction. So you
Well, I'm
might
gonna
could argue
argue that.
that's not a velocity, but
But
it's got some sort of direction, so that's a little bit. We can check our answer. Let's see what they said. 232. All right. Numbers 1 and 3, it said. Yeah, we were right. All right, combining velocities. If, you know,
No,
No, we don't.
our cutoff off at 2:30.
that's fine, sorry. If you're riding in a bus traveling car, that doesn't make sense. If you're riding in a bus traveling east, rather, the bus traveling
Traveling.
car. Yeah.
Oh, I like that.
I was like, that could not be the word. I just don't SIBO. At 15 meters per second, you and all the other passengers are also traveling at a velocity of 15 meters per second east. But suppose you stand up and walk down the bus's aisle while it is moving. Are you still moving at the same velocity of the bus?
Yes.
No. Figure 3 shows how you can combine velocities to determine the resultant velocity.
If you jump and you're in the bus, you jump on the bridge.
All right, so look, here's figure 3, determining resultant velocity. Do you think they're gonna have to do this, Anders? Don't throw paper in my class. Oh, you just flicked it? You think I'm blind? Well, whatever it is you're flicking or throwing.
Another important question.
When you combine two velocities that are in the same direction, we add them together to find the resultant velocity. So your resultant velocity would be 15 meters per second east plus 1 meters per second east is 16 meters per second east. Now, when you combine two velocities in opposite directions, we end up with opposite numbers. So we subtract the smaller velocity from the larger to find the resultant velocity. So the resultant velocity is in the direction of the larger velocity. So if we assign a positive and a negative, we can kind of figure those things out. All right, here is your section review today. You are answering these 4 questions. You can use your notes, you can use your textbook, but you should now have your section review here, and you have about 5 minutes or so to do that.
Good question.
Yes.
If a bus is moving and you jump, are you waiting in the same spot? You move back.
I'm not sure. 1, what is the reference point? Use your notes. We wrote down what it was. Number 2. What 2 things must you know to determine speed? Quickly, what do you need to know to determine speed?
Direction.
No, not direction.
Movement.
Look back at your notes. What are the 2 things you need to know to determine speed? No. Yes. So that's number 2. Number 3 is, what is the difference between speed and velocity? Velocity must have a direction, yes. And number 4.
Number 3.
You're gonna have to go back. Explain why it's important to know a tornado's velocity and not just its speed. So be sure your notes contain numbers 1 through 4 of your section review. Okay? This is for you. It's gonna help you on the quiz. All good things here. Nice job today.